as preliminary to our study of conformal field theory, we began to study ward identities associated with symmetries in any quantum field theory, seen from the point of view of path integrals. Okay, so I went through the main idea of derivation of the ward identity last time. This time I'm going to go through it again, but keeping factors in consonance with Polchinski's conventions, which is going to be a very painful task. But since this is a course, one should try to keep factors. Okay, so let's see. So let me quickly remind you of the idea, and then get quickly to the point where we want to be at. In fact, okay. So if you remember, we had a path integral dx e to the power minus s of x, and then some operator insertions over sigma 1 to over sigma 2. Okay, and then we define a symmetry operation. The symmetry operation as x is equal to x prime, an infinitesimal symmetry operation, plus epsilon times some delta. This operation was a symmetry if and only if, this is our definition, if you plug in this change of variables here, the integrand, and rewrite it as an integral over x prime, we get the same functional form for the integrand. Okay, this was the definition of the symmetry where this was true without any statement about what the operators would do. Okay, now under the symmetry operation, operators in general transform. Okay, so it was a symmetry if the statement was true without any operator insertions. But now let's define the change of an operator as follows. This is O1 sigma 1 O n sigma. Let's say that O delta of On is equal O expressed as a function of x prime. On as a function of x prime. You take this object wherever it is and tailor expand it. Okay, when you make this symmetry transformation. Okay. This thing will be O as a function of x, O n as a function of x prime plus epsilon delta. This will be O n as a function of x prime plus something that's first order in epsilon, assuming it is. So plus epsilon times whatever we get, we'll call delta 1, which will be a function of okay? So O n had been the operator x itself, delta O n would be just delta x prime. If O n had been the operator x squared, we would have got 2 x prime times delta x prime, and so on. Is this clear? This is what we mean by the change of an operator under a symmetry transformation. Whenever I use the symbol delta O n of x prime, this is what I mean. Okay, then last time we went through this little manipulation. We said, well, we know that if we make this change of variables without any operator insertions, and if epsilon is a constant, the integral measure and the action don't change. So now let's look at varying epsilons. Let's look at varying epsilons. Okay, so if we make epsilon a function of sigma a, then what would the change be once we make this change of variable? Okay, and so now let me put in my factor conventions, which are straight. As we argued last time, the integral, ignoring operator insertions for a moment, we'll come back there immediately, but ignoring operator insertions, the measure and the action have to be of the form plus the first order in epsilon, something that depends on the derivative of epsilon. And now we'll choose a convention in factors, we'll say plus I by 2 pi. Plus I by 2 pi integral del A epsilon J E. Okay? And if we're working in a space that has a non-trivial metric, we put a factor of the square root of the metric in order to make everything Lorentz. Lorentz in it. Okay, mostly we'll be working in flat space. We might forget these factors of square root G. But of course, you just go ahead and recognize everything. You do it. Okay, so this is our definition of two things have gone into this. The physics that's gone into this is the statement that the action of the measure don't change if epsilon is a constant. Then any changes will be proportional to the derivative of epsilon. Because if there were more derivatives of epsilon, we could partially integrate those derivatives there. Okay, so and this statement is only being made to first order in epsilon. Okay, so that's the physics, and then there's some convention dependence, which is what factor you put out here. And of course, it will be changed by redefining this GA function, about which we said nothing. This is going to be our convention for what this GA is. This will be our definition of GA.
G is the worldsheet.
Worldsheet metric, correct. Okay. So this is what we get when we perform this variable change without operator insertions. Okay. Now, this epsilon function was entirely in our hands. Okay. So suppose we got a set of operator insertions. These operators are inserted here. Okay. The first thing we can do is choose a region and choose epsilon that support only in that region. Okay. So it's slightly singular, it will be useful for what I'm saying to choose epsilon to be 1 in that region and 0 outside. Okay? In that case, this change of variables does not affect the operator insertions at all. Because the variable changes identity where the operators are located. And the operators are local functions of the x fields. Over sigma 1 depends only on the value of x and sigma 1 and in the neighborhood. Okay? So, that tells us that if we do that manipulation, we take all these operator insertions, they haven't changed, and then we use the fact that the integral, of course, doesn't change under variable transformation, subtract the two, and that gives us the statement that a integral del A epsilon JA, square root G, over any region that does not contain an operator insertion is 0. Then, as we did last time, we can take the statement, integrate it by parts, move the del A, the derivative to JA, and we land up with the conclusion that since epsilon then is completely arbitrary function, okay, we land up with the conclusion that we conclude that del A of JA O sigma 1 O sigma O1 sigma 1 O n sigma n is equal to 0 provided sigma is not equal to any of the sigmas. Okay, this is what we talked about last time. Okay. Any questions, comments about this? Now, there's a more interesting statement that we will use a lot. Okay, when we allow our region over which this epsilon is non-zero, to enclose, just for simplicity, one of the operator insertions. Okay, so let's choose an epsilon that's non-zero over some region that includes one operator insertion, but nothing else. Okay, and as we said, we choose epsilon to be 1 everywhere in this region and 0 outside. Okay, so now let's perform the same manipulation and see what we get. So what do we get? The first thing we get is that the first thing we see is that when we do this change of variables, we get that the partition, wherever this, let's call this quantity C. C is equal to this. So we also have that C now is equal to integral dx prime exponential minus s of x prime. When we got this term, that's the same as before, by where G del A epsilon G A. Okay? Times O, and let's say the operator which is enclosed is the first operator. So this is O1 plus delta O1. There's an epsilon here. Okay? Yeah, so we choose this epsilon function to be epsilon in this region and 0 outside. We want a small parameter so that we can expand everything to. Okay, so that's what this epsilon is. It's the constant value of that function inside this region. Is that clear? Okay, good. And then O2 has not been affected. O2 of sigma 2 over n of sigma n. Now this is been affected. Okay, so C which was equal to this is also equal to this. Now we subtract the two and keep terms at leading order next. Okay, so what do we get? From here we get something simple. We get I by 2 pi, and then we take this and integrate it by parts. So this derivative goes and hits this j. And okay, so let's do that first. Minus I by 2 del a of integral j a of sigma O1 of sigma 1 O n of sigma n. Okay, and this is integrated over sigma. And this whole integral is only over this region. Over this region where epsilon was not 0. So let's call that region R. Okay, plus we get the correlation function of epsilon well, that's this is the correlation of epsilon. So delta O1 of sigma 1 O2 sigma 2 O n of sigma n. We'll see. Is this clear? Then the next step, we use the Stokes theorem, the thing that takes that integral of a total divergence to integral of at the boundary. Alright? So, we use Stokes theorem to conclude that I by 2 pi of j mu dot n mu, where n is the normal vector to the boundary of this region. Outward pointing normal vector to the boundary of this region. And this integral is taken, this is at point sigma, and this integral now is taken over the boundary of the region. Okay, this symbol is often used for the boundary of region. There. Times O1 of sigma 1 is equal to, and correlation function, is equal to correlation function delta O1 of sigma 1 Is this clear? Okay. And then the next step we do some algebra, which, while painful, let me do once or twice just to get our factors of 2 straight. I think this is the first time I'm teaching this course trying to keep track of factors of 2. Let's see if I can. Okay, so now the next thing I want to do is to take this j mu n mu over a contour and write it in terms of complex variables. So we've decided to use complex variables on our worksheet. Okay, so what is j mu n mu? Well, suppose we've got a little different. We're taking j, and we've got a contour along which, the little tangent vector along the contour is the vector dx dy. Okay? Then the integral j mu n mu is the Then what's the normal vector to this tangent that has this? What's the vector orthogonal to this tangent that has the same length as it? Okay, it's very clear that it is plus or minus dy minus dx. Okay, this is a vector that has 0 dot product with the first vector. It's the normal to it. It's clear it has the same length as it. Okay? Now, which side do we choose? Well, we want the outward pointing normal. So, if we're going in, we're doing the integral anti-clockwise, as we will always choose to. If we just had dy, we should get the normal in the dx direction with a positive sign. Okay? So, this thing is corrected with a plus. Okay? So, j mu n mu is the same thing as jx dy minus jy dx. just taken the vector j and dotted it with this thing. Is this clear? Okay? Now, I claim this is the same thing as jz dz minus jz bar jz bar dz bar. This is the same thing as jz dz minus jz bar dz bar, where of course I need to make what is jz? Well, you see z, where this is to be thought of as having an upper index, is equal to x plus I. So for instance, dz is dx plus I dy. That's a usual convention. Okay? So anything with an upper index, any vector with an upper index, okay, so that tells us that jz with an upper index is jx plus ij. Yeah. We should, of course, with x and y makes no difference, because upper is same. Right. Okay. But jz, okay, how does that? That behaves the same way as the derivative with respect to z. Okay? So j little z, so let's remember that d by dz is equal to dx by dz d by dx plus a similar term with y. And x is z plus z bar by 2. Okay? So jz is half of jx plus ij, which is the same as half of j upper x plus ij upper y, because jx and dx. Right? So these are the conventions with which we're working. Okay? Whenever we see a jz with a lower z, if you wanted to convert it to Cartesian coordinates, it's this. If you want to convert it with, if you wanted to write it with wait, have I got my plus minus? It's minus. I think you're right. It's a minus side. Let's check that. Let's check that's from this point of view. So let's work it out completely. So we have d by dz is equal to dx by dz d by dx plus dy by dz d by dy. Now x is equal to z plus z bar by 2. But y is equal to z minus z bar by 2i. Okay? So, jz will have a 1 by I and therefore a minus I. Thank you. Okay. So this is what jz is, and jz bar is half of jx plus ij. Okay, so now it's a simple matter to check that this is the same as this. Okay, let's just once we do it. Of course, there are many more sophisticated ways of seeing it. It's basically the transformation of the epsilon symbol that we're working on here. Okay, but okay, when things are so straightforward, you don't do fancy. Okay, so so this is half. Let's look at this expression. This is half of jx minus ijy into dx plus idy minus jx plus ijy into dx minus idy. Now you can see that the jx dx terms cancel. The jy dy terms cancel. What remains is the jx dx and jx dy and jy dx terms. And I've got a factor of r, right? Yeah, good. So let's work it out. So this is jx dy I times jx dy minus jy dx. Okay, good. So this divided by I, so 1 by I, jz dz minus jz bar dz bar is equal to jx dy minus jy. Okay, clear? Fine. somebody is going to have to remind me of the sign of the equation I talked about. We had an equation that was I by 2 pi. J dot n delta O1 is equal to delta O1. What was the sign, please? Was this sign correct? The sign is correct. Okay, good. So I j dot n is jz. So this thing is 1 by 2 pi jz O1 blah 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 minus 1 by 2 pi. This is dz minus 1 by 2 pi jz bar O1 blah 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 is equal to delta O1 blah blah blah. Okay, now all of this is generally true. Okay, we are going to make a special additional simplification, and a simplification that will turn out to be true in every case that we will use it. You see, we know that this function, whatever it is, apart from singularities that could occur when j hits O1, okay, we know that the insertion of we know that del z bar jz plus del z jz bar inserted in any path integral is equal to 0 apart from singularities where things collide. Now there's one simple way in which this constraint can be met, and that simple way is that this insertion into a path integral was 0 and this term was also 0. Okay, nothing we have derived requires that so far. But of course, it's a special case. It's a special case that might sometimes be true, and will often be true, and that's why I'm looking at it. Okay, in that case, the function which has a j insertion is entirely analytic in Z. Okay, and the function that has jz bar insertion is entirely anti-analytic in Z. This integral here is a path integral, is a contour integral over Z over a correlation function that we have just concluded for the special case is analytic in Z. Similarly, this is a contour integral over Z bar over a correlation function which we have just concluded is anti-analytic in Z bar. But over here, not concluded, just assumed. Okay? In this special case, these integrals can be done very simply using Cauchy's theorem. Okay? These integrals are 0 unless there are poles. Okay? So you remember what we have to get is delta O at the delta O1 at the point of insertion at O. So we want to get something that's non-zero, but only at the point of insertion of O1. But from complex analysis, okay, the way that happens is if these integrants have poles at the location of O1. Okay? At least one of these two integrands must have a pole at the location of O1. And when that is true, the contribution to this integral is 2 pi I times the residue of them. There's a factor of 2 pi here. This minus is cancelled by the fact that it's an anti-analytic integral. See, you actually, with the minus sign, you pick up the residue. Okay? So, the net conclusion is that in order for this to be true, modulo our assumption that J by Jz by itself is analytic and Jz bar by itself is anti-analytic. And when that is true, it follows that I times the residue of the pole in Jz with O1, okay, plus residue of the pole with J Z bar of Z bar with O1 is equal to delta. Okay, all factors agree with my notes, so that's good. Is this clear? So this is the conclusion that we reached very hurriedly last time. I've explained it more, so taking more time this time. It's the same argument, just taking more time. Is this completely clear? So what we have done is that in this particular case of a situation where the symmetric currents, the analytic parts are, the Jz is analytic and Jz bar is anti-analytic, we have related the transformation properties of operators to singularities in the correlation functions between this operator and the current that generates the symmetry. Okay? So what does the statement mean? The statement means that if you compute the correlation function of J with an operator O1, there must be a singularity in this correlation function. This correlation function must blow up as the insertion point of J approaches the insertion point of O1. There are many kinds of singularities. The only one that we're sensitive to is the pole. There must be a pole and with a determined residue. Is this clear? Okay. Now, immediately we're going to apply this this analysis to a particular symmetry of great importance, namely the symmetry under space-time translations. Okay, and we will apply this analysis to a conformal theory in this special case. Okay, so. Fine. So the first thing we want to understand, well, this is a bit of an aside, but it will be a useful aside. We want to understand that there is a second. Well, how do we generate the symmetry, the current that generates space-time translations? We use our usual mode of procedure. If you want, perform an infinitesimal translation, and then you make that space-time dependent. Okay. So let me first start with the definition. Let me define that suppose I perform a translation by epsilon mu, okay, in the direction epsilon mu, then I will get a symmetry current. Let me define, and now some I that Polchinski puts there first. Reason of reasons unknown. So it'll be in. Let me get my conventions matching these. Which way? Just sorry. Okay. Let I any mean period. Okay. So what are we saying? You see, suppose we translate in the x direction, in a particular direction, we have a current. We have symmetrical translation in that direction. Suppose we translate in the y direction, we have another current. Now, since x and y transform like a vector, instead of having a vector of currents, we'll have a tensor of currents. Because we've got two indices. The index of which index of the current and which direction we're translating. Okay? So this is the precise connection between the tensor and the vector. We've got a tensor which is going to be called the stress energy tensor. Okay? And if you want the current for translation in the n mu direction, the epsilon, let me call it n mu, so the normal vector, you take the stress tensor, multiply by I times n mu, and you've got some current. That current is the local current corresponding to translations in the n direction. Okay, this is fine. So, now what we're going to do is to find a convenient another expression, a second independent and oftentimes more useful expression for this translator of for T mu nu than the expression of than the implicit operation of just acting with the Noether procedure. Okay, in order to do that, basically what we're going to do is to use a clever trick to implement the Noether procedure. Okay, so first let's start. Suppose we wanted to implement the Noether procedure. Okay, well what would we do? Well, basically what we do is to make n mu space dependent. Okay, so what we do is to make a change of variables, which is delta x mu is equal to x. Well, x mu is equal to x mu prime plus epsilon mu of x. Okay, and the current in question will be, the coefficient of the derivatives of epsilon mu. I could do this in many steps. I could say epsilon times n mu. N was a constant vector, and then that would give me the current for that particular translation. But it's faster just do it all at once. Okay, if you get confused, you can do it that way. Is this clear? Okay, fine. Now, if we make such a change of variables, what we're supposed to do is to see how the path integral changes and identify the coefficients of the derivatives of epsilon mu as terms of the stress tensor. But we know something about it. You see what this is? It's just an infinitesimal diffuse. A small change in the coordinates of our base manifold. Now, we know of an operation under which the action, and presumably the measure, if you define a measure in a diffeomorphically inverted way, the action of the theory does not change. And this action is performed the diffeomorphism not just on coordinates but also on the metric of your theory. Okay? If you make this coordinate change and you change the metric appropriate to this coordinate change, okay, then as a function of the new metric and the new coordinates, your action will be the same as it was as a function of old metric and old coordinates. Okay? That's of course just a statement of general coordinate invariance. Is this clear? However, according to the Noether procedure, that's not what we're supposed to be doing. What we're supposed to be doing is just making this change of coordinates, not touching the metric, and seeing how the action changes. But since we know that there's an operation under which a combined operation of two things which leave it unchanged, instead of making this change of coordinates, we can make the change of metric. Okay? And put a minus sign, and that will give us the change in the action. Okay? So we know that. So what we know is that making this change of coordinates, we want to ask how the action changes. The answer is the change. So suppose we've got the action which is equal to well, the answer is simply minus of del S by del G mu nu, okay, times the change in the metric that would have been induced by this coordinate change. Now, what is the change in the metric induced by such a coordinate change? Okay, it's easy to work out. It's also, once you've worked it out a couple of times, you generally remember this. It's got a fancy name. It's the Lie derivative of the vector field. But about flat space leading order, the answer is simply del mu epsilon mu plus del mu epsilon. This is the change in the metric induced by this coordinate change. Okay, so the Noether procedure asked us to find what the change in the metric was when we made this coordinate change. Using this fancy trick, we know the answer. This is the answer. Now, of course, G mu nu is a symmetric tensor. So this contraction with this and this contraction with this is the same thing, just a factor of 2. Okay, so this is minus 2 delta S by delta G mu nu. del mu epsilon mu. Okay? If we had written this S as an integral over a local quantity, this would have been the integral. This is more accurately. So the integral of L d mu epsilon mu, where S was equal to integral. Okay? Now the rest is, so we've got to answer, the rest is painful tracking through conventions. Okay. According to our procedure, we should take the coefficient of del mu epsilon mu. Okay, let me just remind ourselves about what we wanted. We said that we'd start with e to the power minus s, and that goes to e to the power minus s plus I by 2 pi del mu epsilon, del mu epsilon times g for any current. Okay, in this particular case, for epsilon itself carries an index. This is this is true for any current. Now, when epsilon itself carries an index, this is equal to epsilon nu times t nu mu times I, because J was this. Right? Okay. Now let's take the minus sign out overall. So this is a change. So I times I is minus. There's a minus in the S. So this is a delta S, which is equal to plus of 1 by 2 pi del mu epsilon mu times t nu mu. But we've seen the delta S is minus of this, and so we conclude that T and of course we can raise the lower indices at will. So T mu nu is equal to del L by delta G mu nu times minus 4 pi. Let me check. Yeah. Okay, good. Right. Now, you're right. You see, because what we wanted here was this times square root g. Okay, so really we get a 1 over square root of g. Well, let's say we get a Euclidean square root of g. You're completely right. Okay, so thank you. If we put in a full definition of the square root g here, we would have to identify this. Okay, very good. Okay, so now we're working with Polchinski's conventions. I really cannot figure out why he put the I for a general current and then removed it for a stress tensor. It's just painful. But anyway, it's probably like he's trying to match with other people's conventions. Somebody should just rewrite conventions once and for all. But anyway, so this is what we got. So the stress tensor has this nice this nice interpretation. I mean, it has this nice alternative formula. Okay, and the alternative formula is that it's the derivative of the Lagrangian with respect to the metric. And this Lagrangian, mind you, includes the square root g. Derivative of whatever enters the S is integral n. not the integral square root g. You have to differentiate the square root g. Okay? Fine. So far, everything we've said has been totally general. It applies to every order theory. It applies beyond 2 dimensions. Okay. But now we're going to specialize. Now we're going to specialize to 2-dimensional conformal. Okay. So, what can we say about a 2-dimensional conformal? Well, let's stick to working in flat space for a moment. We're in flat space, and the fact that the theory is conformally invariant, okay, implies that just the fact that the theory is scale invariant, just the fact that the theory is scale invariant, conformal invariance in particular implies scale invariance. Invariance under scaling of coordinates. Okay? That implies that the partition function of the theory, does not change under a scaling of coordinates. Okay? But a scaling of coordinates can be compensated for by you scale coordinates, you can rescale them back by performing a coordinate change. That just what that does is rescale your metric. Okay? So the theory being invariant under scaling of coordinates is the same thing as the partition function being invariant under scaling of the metric. Is this clear? Because, just to say it again, because if the theory is generally coordinate invariant, and if you scale your coordinates, you can undo that state of scale by coordinate change. What that coordinate change does is change the metric. Okay? So, the derivative of the Lagrangian, inside the path integral, insertions of this object inside the path integral, derivative of the Lagrangian with respect to the metric must vanish for those changes in the metric that are proportional to the original metric. Is this clear? Okay? So, what we conclude is that del L by del G mu nu times G mu nu is equal to 0. Okay? And therefore, G mu nu times G mu nu is equal to 0. So we conclude that in a conformal field theory, the metric in particular, the stress tensor in particular stresses d mu mu is equal to 0. This general argument might sound like it applies to, beyond flat space. We will see that there is a quantum subtlety in this argument. That it cannot be both true in flat space and all spaces in any conformal field theory. We'll revisit that very soon, perhaps by the end of this lecture. Okay, but I just want to warn you that this conclusion is not going to be too strongly true. It's the naive conclusion that you reach when you try to understand what's going on, at least in flat space. Okay, we'll come back to the subtlety a bit. So we've concluded that if we're dealing with a conformal field theory, so far we've not specialized in 2 dimensions, any conformal field theory. And scale there. The trace of the stress tensor must vanish. Okay. But one can make this argument at various levels of sophistication. Okay. This is good enough for now. Okay. But now, let's specialize to 2 dimensions. Okay. So what does this equation imply? This equation. Okay. Also, of course, the stress tensor is conserved. That is of course true. So we have d mu nu is equal to 0. What do both these statements mean, by the way? Both these statements mean what these statements mean really is that any correlation function involving these quantities and other operators is 0, at least away from coincidence points. Okay? We know that this statement is not true at coincidence points. We found the correct version of that statement. That's the order identities. We'll use that very soon. Okay? There could be trouble with this statement also at coincidence points. We'll come back to that. But certainly if you insert this operator inside a correlation function and you stay away from other operator insertions, we get 0. That's the conclusion we're confident. Okay, good. So, now let us see what we can say about correlation functions, therefore involving the stress tensor, staying away from insertion points at the moment. We'll start approaching insertion points in a very small amount of time. Okay, so let's work this all out in 2 dimensions in complex coordinates. So this quantity in complex coordinates is the statement that T Z Z bar. Can somebody tell me why?
T Z bar Z bar is well brought down Z bar.
Yeah. So what is the statement? This is T Z Z plus T Z bar is equal to 0, which means T Z, which means T alpha Z G alpha Z plus T beta Z bar G beta Z bar equals 0. That's what the statement means. But the only non-zero component of the upper metric with a Z index is the one in which the other index is Z bar. So this thing is a Z bar. And similarly here, so you get some factor times TZ Z bar. Okay. So of the 3 components of the stress tensor, TZZ, TZZ bar, and TZ bar Z bar, one is just set to 0 by scaling methods. Here's my traces of the stress tensor. Fine. Now what about the others? What about the conservation equations? So the conservation equations are dz tz bar z plus dz bar tz z equals 0. That's one conservation equation. Can somebody tell me how I got this from conservation? So if I were to write the equation as del mu t mu nu equals 0, what values of indices have I chosen? What have I chosen nu to be doing this equation? Z. Right. So this is the index nu. And this is the same contraction. This is that contraction. Okay. But this equation can be simplified because we know that T Z Z bar is equal to 0. Okay. So since it's 0 at each point, its derivative is 0, provided we stay away from insertion points. We have to be careful about insertion points. Provided we stay away from insertion points, this is just 0. Okay, so we reach the conclusion that del Z bar of TZZ is equal to 0. So inside correlation functions, the correlation function of TZZ is an analytic function of the point of its insertion, as long as you stay away from, at least as long as you stay away from operators. Is this clear? Similarly, if you let the free index be del Z bar, you can do del Z bar of TZ bar. Fine, del Z. Okay, so TZZ, Z bar is an anti-analytic function of the position of its insertion. So, you see, by doing almost no work, we've learned a lot about correlation functions of stress tensor insertions in a conformal field theory. We've learned that the correlation functions are 0 if you insert a TZZ bar. We've learned that if you insert a TZZ or TZ bar Z bar, respectively, you have an analytic or anti-analytic function of the point of insertion of this correlation. Is this clear? Fine. So now we're going to learn more. We're going to learn more because now we're going to scale, overcome our fear of approaching operators, try to approach these operators and see what we get. Okay? So, it would be most useful before we do that to find the Noether currents for the infinite other symmetries we have in the problem. You see, we're dealing with conformal field theory. Of course, translations are symmetric in this problem. But you remember that there are a whole infinite class of symmetries in this theory, namely coordinate redefinitions by any analytic function of z, by any anti-analytic function of z. Okay? I'm not even sure we said this, but this is just the analytic statement we made. Namely that if you take sigma plus and make it a function of sigma plus, and sigma minus and make it a function of sigma minus, that induces a conformal change. Let's just check that here. The metric is dz bar. So you take z to any function of itself, and z bar will be complex conjugate function of itself. Clearly what you get is you retain the fact that it's dz bar and some function of z. And therefore it's conformally related to the original metric. Okay? So since we're dealing with a conformal field theory, this is a quantum field theory in which all such coordinate changes, remember, with no compensating change of a metric. This is crucial. Any coordinate changes the metric, you also change the metric. But that's not telling you very much, because changing the metric is changing your Lagrangian. Okay? This is meant to be if you've got conformal field theory, all these changes of coordinates without any compensating changes of the metric should be a symmetric field theory. Okay? Let's see why that's true and determine the Noether currents corresponding to these coordinate changes. Okay. Okay, so though we can do it more generally, I think it's conceptually clearest to do it one at a time. So let's make change of variable z is equal to z prime plus epsilon z prime to the power n. And z bar is equal to z bar prime plus epsilon bar, of course, z bar prime to the power n. Now remember, we're dealing with complex variables. So epsilon here is a complex variable. So though I've written it like this, the way I've written it looks like there's one symmetry, there are actually two symmetries. There's a symmetry corresponding to the real part of epsilon, symmetry corresponding to the imaginary part of epsilon. Okay? So this is two symmetry transformations. It's often algebraically more convenient, instead of dealing with the real part of epsilon and the imaginary part of epsilon, to deal with epsilon and epsilon bar as the two independent coordinates. Okay, I want to emphasize a clarification. It's not true, of course, that epsilon and epsilon bar are independent coordinates, in the sense that if you know epsilon, you know what epsilon bar is. That's of course true. What I'm doing is the former thing of changing variables from two independent things like the real part and the imaginary part to real plus I times imaginary and real minus I times imaginary. Okay? There are two symmetries here, and I'm parametrizing it by real plus I times imaginary and real minus I times imaginary. That's what I mean by saying that we were independent, coordinate symmetry transformation. The number is 2, I can parameterize it anyhow. Okay? So, as we will see, it will always be convenient to think of analytic and anti-analytic as independent to the extent that we can. It's in the sense that the statement is true. Okay? So we're looking at the symmetry. Instead of thinking of real part of epsilon and imaginary part of epsilon as two independent parameters, think of epsilon and epsilon bars as two independent parameters. Just by making the appropriate linear transformation. Okay? Good.
But if somebody is, for example, when we are actually doing the operations, so one is independently varying z and z bar. So it might seem like as if there are 4 independent parameters.
But one is not independently varying z and z bar.
Finally, one is putting.
Yes, because when you say you change z, you also automatically change z bar. You just dump that change into the complex parameter. Okay, so this often leads to confusion. A lot of people say things that are just totally wrong. The variations Z and Z bar never independent. Just that there is a complex parameter in there. That's the only contextual statement. Everything I do, I'm going to find the symmetry current for varying epsilon and the symmetry current for varying epsilon bar. Okay? What that really means, so I found the symmetry current for varying real part of epsilon, which is the sum of these two, and the symmetry current for varying the imaginary part of epsilon, which is the difference of these two. But the point is, once I've got some symmetric currents, any linear combination of it is also symmetric currents. So I might as well stick with varying epsilon and epsilon bar. See, that's all that it means. Okay, Z is always the complex conjugate of Z bar. There's no sense in which it's not. Okay. Okay, very good. So let's take this coordinate change. Let's take this coordinate change and see, identify the symmetric current by using the Noether procedure. Now we've got very smart. See, we said, whenever we have a coordinate change, we can implement the Noether procedure by performing the compensating change on the metric. Right? So firstly, this is a symmetric transformation. So in order to get something with the Noether procedure, we must take our epsilon and make it a general function of coordinates. So we must take our epsilon and make it a function of Z and Z bar. And here this is epsilon bar, which is a function of Z bar and Z. We must make it the most general possible function of coordinates. Therefore, a function of Z and Z. Now we've got this coordinate change, and we want to see how the action has changed. But the action has changed minus the amount it would have changed by making the metric variation. Right? So the change in the action is equal to minus of del L by delta G mu nu times the change in the metric, and we use our lower formula. Okay? Times let's call this thing delta Z and call this thing delta Z bar. Make notation simple. So times del mu delta x mu plus del mu delta x mu. But let's work always in flat space, so we don't have to get the square root g factors, right? Square root g. Okay. Now this guy, by definition, is minus d mu nu of del mu delta x nu plus del mu delta x. Thank you. Minus, so this plus, and which way does the total go?
It becomes plus or more.
Thank you. Now let's see if I can get the final answer right. Okay, good. Now, we know what our delta x mu's and delta x mu's are. Just since we know it with upward, let's write this as plus 1 by 4 pi and t mu. Okay, now this thing is twice b. This is symmetric, right? So I don't need to keep track of both of these. So I make this 1 over 2 pi. And this. Okay, and right, I'll use that. But let me just put this in a nice, way so this I can write as t mu nu del mu delta x nu. Okay. So now this is 2 pi. So this is plus 1 by 2 pi times t z. Now t z z bar, where both go down to 0, which means t z z 1 up 1 down, or t z bar 1 up 1 down, okay, are both 0. Okay. the only, if I put a z here, the only index I can have here is a z bar. So T z bar del z delta of z bar plus T z bar z. T z bar z del z bar delta z is equal to 0. I mean, no, this is the derivation of the action. Okay? Now let's put in what we know about what delta z and delta z are. You see, what we've done here is an analytic derivative of delta z bar. But delta z bar had an anti-analytic function times the arbitrary function. This derivative does not hit the z bar to the power n. That's why it was symmetric. You see, the change in the action is 0 if this epsilon is constant. That's what we're saying. So we verify. The first thing we've done is a verification that this actually is a symmetry. Okay? So let's work this out here. So this is plus 1 by 2 pi. Now T z bar. Then this is what? This is z bar to the power n times del z of epsilon bar plus Tz bar z z to the power n del z bar of epsilon. Okay, now we're home. You see, our procedure, the North procedure asked us to identify the coefficient of the derivatives of epsilon and epsilon bar as the currents corresponding to the transformation induced by epsilon and epsilon bar. So we see, let's first do the guy with epsilon. We see that we see that the guy with epsilon has only a z bar derivative of epsilon. Yeah, there's no z derivative of epsilon. The z bar derivative of epsilon and the z derivative of epsilon bar. So if we're interested in the symmetry corresponding to the epsilon transformation, which I remind you just means the symmetry for the real part of epsilon plus I times spin. Just combination. Okay? The first thing we conclude is that Jz for the symmetry for epsilon is equal to 0. Because it's Jz would have been the coefficient of del z of epsilon. But there's no del z of epsilon. Okay? And Jz bar of epsilon is equal to, now of course we have to say what our definition of Jz bar is. Okay? We put in the I. You know, we'll put in the same I that we put in for translations. Okay? So I'm going to define my Jz bar without any. You see, we have the 1 over 2 pi that we had in the general express tensor thing. But you remember that in going from the general definition of the current to the current for translations, we put in an extra I. Since translations is a special case of conformal transformations, you want to put in the same I for everything else. So when you put that I in, I'm not going to bother to try to check that. I'm getting the right sign. I'll leave you to check that. That's just a statement that this is Tz bar z times z. Okay? So, Tz bar z times z to the pi.
Okay, and then z will not.
No, there's no I because okay, let's say this again. Had we been defining our current the usual way, there would have been an I. But remember, in defining the stress tensor, we put in an extra factor of I. Let me say this again. Let me say that what I'm going to do is to define, let me try to get this out. What I'm going to do is to define the current with respect for conformal transformations to be such that
If you the reason why we got that right.
No, you see, in the usual definition of the current, the change in the action had an I. Delta S was equal to I by 2 pi.
It was minus I by 2 by del A epsilon.
Del A epsilon J. This was the usual definition. So if we were using the usual definition, now we would have an I. Because we've got 1 by 2 pi, but without an I. Okay? But the current corresponding to translations was scaled by an extra factor of pi. Let's remember.
I think that I was introduced, because this I was there.
Right. So the I was introduced in order to make the definition effectively for translations without an I. You see, the most general definition had an I, and then we put an extra factor of I for translations. The general definition of currents said the change in the action has I by 2 pi with some plus minus times this minus. Please take this.
Okay, so we just got this. Okay, and we check the title is this. Okay, and if I just identify the corresponding J, I just get that. I just understand that.
If you identify the corresponding J, you get the I. Exactly. But you see, now let's just look at this point. You see, the variation in the action has no I's in it.
Yes.
And the stress tensor has no I's in it.
Yes.
So the stress tensor is related to the variation without an I. This stress tensor is related to this variation without an I. Okay? So if we use the same conventions, we've got the variations with no I. The current corresponding to these things, which is like the stress tensor, should have no I. Okay. Okay, there are two objects.
When n is equal to 0,
When n is equal to 0,
this should go to the translations.
this should go to the translations, exactly.
And there is an I there.
No, there's no I. You see, the translations, the current corresponding translation is just the stress tensor.
Okay.
I'm sorry. It's utterly unimportant. Because it's a matter of conventions. I'm just trying to follow Kuczynski's conventions, which unfortunately are convoluted. Okay? But in some conventions, there's no way. Okay. Fine. But, so now let's do this whole thing with lower indices. Okay? What we've got is J epsilon Z is equal to T below both sides. Z pi. J epsilon Z bar is equal to 0. Okay? And we've got J epsilon bar Z is equal to 0. J epsilon bar Z bar is equal to Z bar bar n T Z bar Z. Is this clear? So now we see that conformal transformations with respect to epsilon and epsilon bar are of the special class of symmetry operations that we dealt with earlier in this lecture. Because Jz is an analytic function of Z. Tzz is analytic. Z bar n is analytic. Therefore the insertion of this is analytic. And Jz bar is an anti-analytic function. It happens to be the anti-analytic function 0. Okay? So epsilon transformations, the symmetry current, falls in conformal transformations with respect to the analytic conformal transformations, fall into the class we talked about last time. Similarly, so do the anti-analytical work. Okay? So for conformal transformations, the word identities turn into a statement about this trick of converting word identities into statements about residues of poles using Cauchy's theorem works. That's the principal reason we introduced this trick, because conformal transformations are going to be very important. Is this clear? Fine. So now let's use this trick. Let's use the trick that we let's use the result of our previous analysis. The result of our previous analysis was that the residue of J with the operator plus the residue of J bar with the operator has a singularity which changes with the operator times 4. Okay? In our general analysis we also had an I, but since our conventions differ from the general analysis by an I, we won't have an I. Okay? So, the net result is, I'm not going to try to justify the sign. I'm not sure. It will take years. Okay. Then the residue of z to the power n, and now, I've done it for z to the power n, but since it works for z to the power n, it works for any analytic function of z. N could be any positive, negative number. So, residue of epsilon of z times and tz, well, let me just say more clearly. We conclude that epsilon of z times tz acting on O of inserted at any point, but let me choose it to be 0 for convenience.
Tz is tzz.
I'm changing notation now. Tz is tzz, and when I want tz bar, tz bar z bar, I'll call it t bar of z bar. Okay. So epsilon of tz, that is O, could be made up of many things, but it has a piece which has a pole. 1 over z minus 1 over z, and the residue of that pole is delta O under the conformal transformation. Okay? Similarly, we work that epsilon bar of z bar times t bar of z bar, O of 0, 0 is equal to okay? There's no ambiguity here. It's not like we've got some confusion only of the sum of two things, because the first one refers to epsilon transformations. The second one refers to epsilon bar transformations. These are two separate transformations. Is this clear? Fine. Now, this general statement about singularities and correlation functions has a name. It's called the operator. It's part of what's called the operator product expansion. We'll study the operator product expansion in detail on Friday. Okay? I just want to introduce the name so that you heard. Okay. Now, what I'm going to try to do, this is true for any conformal transformation. Let me now see what I can deduce about the operator product expansion. The singularities in correlation functions when operators approach each other. Okay? What can I say? More concretely. Okay. So in order to know that, I have to know what delta O is for operators under conformal transformations. Okay. We don't yet, for a general operator, we don't know how it transforms. We don't yet know how it transforms under all conformal transformations. But we don't know how it transforms under some conformal transformations. So firstly, any local operator under a translation changes by a derivative. Okay, so before that, let me do some formal manipulation. So I'm going to do all my manipulations with the top line. Every manipulation I do with the top line can be repeated for the second line. I'm not going to bother to do it in class. Okay, so let's suppose that epsilon of z, well, epsilon of z is anything, it has some Taylor series expansion. Okay, so it's sum over n del n of epsilon by n factorial z to the power n No, there's no choice. You see, what appears here is the z bar derivative of epsilon. That tells me that the current corresponding to epsilon has only a jz bar with an upper limit. And therefore only a jz with a lower limit. Okay? And what is that component? Well, it's this. So there's no choice. I'm just reading off the components. Is this clear? Okay. So say I take epsilon and I take a series expanded. Okay. And okay, so I take epsilon and I take a series expanded. So I'm specializing to those epsilons that have a Taylor series expansion. It's good. I could look at things that have singularities, but we'll deal with those later. Okay. So I get the epsilon and I take a series expanded. And suppose Tz with O and the following singularity structure correlation functions. Namely, it's sum over n an by z to the pi plus 1. What this equation means, we will understand better in the next lecture. See, what this equation means really, let me just say in words that we'll understand better. You see, this is a statement about correlation functions. Now, you might ask about which correlation function, because you told me about what T and O are doing, but there may be other correlators in certain new forms. So what do you say? It's a remarkable property of quantum field theory that if you have some operators inserted sort of far away, we'll see what it means, what far away means next. And you've got two operators nearby. Then the dependence of this correlation function on the distance between these two operators is independent of what other operators you have inserted in your okay? And therefore this becomes an absolute operator. I mean, a statement that is true. You don't have to say about which correlation function it will be. In any correlation function, as long as these two operators come near to each other, this statement will be true inside the path integral. That instead of inserting this times this, you can insert this path series. Okay? This is a remarkable feature of quantum field theory. This is called the operator product expansion. Okay? We'll understand that better next class. We'll derive it for conformal field theories. But for now, we're not trying to be so sophisticated. Let's just assume that in some intuitive sense you understand that this is true. Okay? Now, let's combine these two statements. Let's combine these two statements and this statement to see what we can find. You see, what we want is the pole. The pole comes when we hit when this n is equal to that, because we want 1 over z left over. Okay? So we conclude that delta O must be equal to sum over n del n epsilon by n factorial times n. Okay? So what have I said? I said that if we perform a general conformal transformation parameterized by epsilon, and if the operator product expansion between T and O has this general structure, then for consistency with this statement, it must be that the change in the operator under a conformal transformation parameterized by epsilon is given by this formula. Is this clear? Now, let's apply this formula. Let's apply this formula to certain special cases. Let's first take epsilon to be a constant. Okay? So, in that case, all the derivatives of epsilon except 0 are 0. Okay? So, under epsilon being a constant, delta O must just be a 0. Okay? But any local operator under translation shifts by its derivative. Okay? So we conclude that del O, that for any local operator, A0 is equal to del O. Now, let me say this again. this is true. This statement is true for any operator which under a conformal transformation parameterized by epsilon changes by delta. Now, while it's a true general statement, it's not very useful so far because we don't know how operators change under an arbitrary conformal transformation. But let's look at those conformal transformations which we do understand. We do know how operators change. Let's look at the simplest conformal transformation, namely a translation. Under a translation, how does a local operator transform? Well, it just translates. So, infinitesimal translation, it changes by its derivative. Right? Because O at Z goes to O at Z plus delta Z. It's constant, so it's just clear? Okay? So, the change under epsilon being a constant must be, delta O must be the derivative. But according to this formula, the only term that contributes is when n is equal to 0. Because all other terms are 0, because del n of epsilon is 0. It's constant. That's an A0 is delta. Okay? So, let's say in slightly more invariant terms what we found that when we take Tz and take any operator O, there is a pole in this operator product extension. That's always true. Okay? And the residue of that pole is universal. It's the derivative of operator divided by Z. Because that was what A0 was. It's the coefficient of 1 by Z. Fine. Well, that was nice general statement which is true of Mach problem. In this fancy setting, implementing the fact that T shifts things if integrated over space. Okay, but now it was conformal field theory, so we know more than just this. Apart from knowing how operators change under translations, we know how they change under rotations because they transform in a certain spin. So let's say we take every operator in the theory and find a basis of operators such that the operators have definite spin. Okay, so we know that, but because we're working with conformal field theory, we can also ask for the operators to be eigenstates under scale transformations. Now, this is a very intuitively plausible statement, what I made. However, next time we will prove it. Like in a two-dimensional conformal field theory, you can use the state operator map to prove it. Turns out to be isomorphic to the statement that in any Hilbert space, you can always find a basis that is diagonal, that is diagonal for the Hamiltonian, which we know is true. Okay, so how we should operate. Okay, so let me say what I said. The first statement about the derivative, the T with O being derivative of O with Z, is true for any local operator. Now, the next statement I'm going to make will not be true for any operator. However, in the space of all operators, it is possible to find a basis such that the statement I make will be true for every basis element. This is analogous and in fact will turn out to be the same as a statement that while not every state in a Hilbert space is an eigenvector of the Hamiltonian, it's always possible to find a basis of states in the Hilbert space that is such that the basis vectors are eigenstates. Okay, so what I want to say is that as I will prove for you next time, this is one of the beautiful things about dealing with two-dimensional conformal field theories. All these deep general statements about quantum field theory that after 30 years of experience people have learned to trust but don't really know why are true. When we're dealing with two-dimensional conformal field theory, you can prove all of them. You can just see why they're all true. This is really a beautiful simple example of it. And we'll prove it next class. Okay? So you won't have to take anything I say on faith. But wait till next class. Let me just proceed till then. Okay? So what I want to say is, let us suppose that you believe me for a moment that it's always possible to find a basis of operators that are eigenoperators under scale transformations and eigenoperators under spin. The second one I think 90 quite closer to the first person. Then we will go through. What does that mean? Well, what is the coordinate change that generates spin? The coordinate change that generates spin is rotations. Rotation is x dy minus y dx, and we've already checked algebraically that this is the same thing as z dz minus z bar dz bar. Okay, that is z dz minus z bar dz bar is very clear, because what a rotation does is rotate z in one way and z bar in the other way. So every time you see a z, you replace it by e to the power I alpha times z. Every time you see a z bar, you replace it by e to the power minus I alpha times z bar. And the infinitesimal version of that statement is the operator z dz minus z bar dz bar. Okay? So rotations are generated by z dz minus z bar dz. These are rotations. What about scale transformations? Taking every coordinate and uniformly scaling it. What generates that? Somebody? Exactly. X mu del mu, which is z dz plus z bar dz bar. Okay? So let us deal with that basis of operators. I emphasize again, we will prove that it's possible to find such a basis, always. Which are ideal states under these two operations, that is transform homogeneously, okay, under these two kinds of conformal transformations. Okay, since is now you've already seen by experience that it's always better to deal with analytic and anti-analytic things. So instead of dealing with this and this, we just deal with the sum and difference. Okay, so. So definition. An operator is said to be quasi-primary of definite weight under scale transformations and spin. If its transformation of weight h bar, if under z dz, so under the by z dz I mean the transformation epsilon z equals z epsilon bar z bar epsilon bar. Okay, delta O is equal to h times O plus, but there are two reasons an operator changes. Firstly, because of scale. Secondly, because you change the coordinates inside. Okay, now you've changed the coordinates inside plus. You've changed by a times z, so this will be z there. Well, let's do it at 0. So delta O at 0 is equal to this. Okay, and similarly delta bar O is equal to h bar. Is this clear? Okay, this is a definition. If you know what h and h bar is, the spin is simply h minus h bar, and the weight under overall scale transformations is h plus h bar. So these are physical interpretations of all. Okay, so now the next question we're going to ask is what else can we say about the operator product expansion between the stress tensor and not an arbitrary operator but an operator that is quasi-primitive. Okay, so that's very simple. You see, we now know what delta O should be when epsilon is z. We're doing it all at 0. So the only element that's non-zero is the first element. So that tells us what A1 is. Okay? It tells us that A1, so when the operator is quasi-primary, we conclude that T of Z O at 0, okay, is equal to T of Z O at 0 is equal to H O by Z squared plus del O by Z plus da 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 plus da. And similarly, bar of Z bar over 0 is equal to plus H bar O Z bar squared plus del bar O Z bar. Okay, this statement is only true, it's not true of all operators, it's only true of quasi-primary operators, operators that are definitely H in each part of the scale. Okay, any questions or comments before we continue? Fine. Now, to end this lecture, what I'm going to do is to work out what the operator product expansion is, not between the stress tensor and any operator, but the stress tensor and stress tensor itself. Okay? So everything that we said in general goes through. Okay? Everything that we said in general goes through. Okay, the stress tensor. So, suppose we wanted to compute Tz of T0, we would find this is 2 times T of Z. It's 2 because both weights of the stress tensor are 2. The weight on the scaling dimensions, scaling is 2 because if you take a stress tensor and you integrate it over space, you must get something which is energy, which is dimension 1. The integral over space is dimension minus 1. So this thing was dimension 2. So stress tensor must have weight 2 and also spin 2. The usual famous reason that, well, it's a spin 2 object. Symmetric 2 tensor. Okay? So this is Z squared plus del T by Z plus da 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 plus da da da. Similarly, an equivalent statement for the anti-analytic stress tensor. Okay, now what I want to do is to see what we can deduce about the plus parameter. Okay, so what can we deduce about the plus parameter? Well, again I'm going to invoke a few facts that you may not be familiar with, but which we will prove either in the next or the next class after that. And, well,